what is anomaly detection? Anomaly detection is a technique used to identify unusual patterns that do not conform to the expected behavior, and they are often called outliers. It has many applications in different fields such as in business, in intrusion detection, which is relevant to identify strange patterns in the network traffic that could signal a hack, in system health monitoring, which is about spotting a malignant tumor in an MRI scan, in fraud detection, in credit card transactions, and fall detection in operating environments. So now the question is, what are the anomalies? An anomaly or an outlier is any data point which differs greatly from the rest of the observations in the dataset. A real-life example could be when a student's grade averages over 90%, while the rest of the class averages around 60%. Another example is that while analyzing a certain customer's purchase patterns, it turns out that there is suddenly an entry for a very high value. The very different data points in these two examples are considered as anomalies or outliers. So let's see, why do outliers even exist? There are too many reasons for that. It might be that the machine or the data analyst made an error in the measurements or while entering the data. It might also be intentional, since some people really don't want to disclose their real information, so they can easily intentionally produce outliers by entering wrong data. Another important question that comes to mind is that, why do we need to detect these outliers? Why not let them be there in the data? Actually, we need to detect these outliers since they affect the results of the analysis and might impact our final decision. But we must also keep in mind that not all of the anomalies are bad data points for the analysis. They might indicate something interesting which can lead to discoveries, for example, novelties in the research. There are two types of anomalies, univariate and multivariate. If the anomalies have extreme values in only one direction or one feature, they are considered as univariate. But if they have extreme values in several features, they are called multivariate. There are mainly three categories of anomaly detection methods. The first one is supervised anomaly detection, in which we train a model based on two classes of data, normal and abnormal data, and try to detect the abnormalities. The second group is called unsupervised anomaly detection, which we will focus on in this section. In this method, we assume that most of the data is normal, then we try to find the abnormalities. The third group is called semi-supervised anomaly detection, in which we train a model based on the normal dataset and test the likelihood of a test sample to be generated by that model. Here in this slide, you can see different types of algorithms and methods that are mainly used for anomaly detection. These techniques include density-based methods like k-nearest neighbor or KNN, the one-class support vector machine, the autoencoders, the Bayesian networks, the hidden Markov model, the statistical approaches, the cluster-based methods like k-means, the angle-based outlier detection method, and the isolation-based outlier detection. In this section, we are going to explain three of the most common methods of the anomaly detection: the statistical methods, the density-based anomaly detection, and the one-class support vector machines. In this slide, we are going to explain about the statistical methods that are used in order to detect the outliers. In this method, we can detect the outlier, which is defined as a data point that lies far away from the mean, the median, the mode, or the quantile of the data. A simple example is that the anomaly is defined as a data point that deviates from the mean by a certain standard deviation. Consider the data as a time series, so the mean is the moving average. Taking the moving average is equal to convolving with a rectangular signal in the time, which is equal to multiplying by a low-pass filter in the frequency domain. The drawback is that if there is noise in the data, that noise would be similar to the anomalous data, and that similarity would impact the mean or the moving average. Thus, it would be impossible to detect the anomaly in this situation. Since we have noise in the data, which is similar to the anomalous data, this anomalous data can also be considered as a part of the noise, and it might be impossible to detect it. The second method that we are going to explain in this video is called the density-based anomaly detection method. In this method, the assumption is that normal points occur around a dense neighborhood and abnormalities are far away. This method is mainly divided into two groups, KNN and relative density of the data, local outlier factor or LOF. Here we are going to explain more about this LOF method. In the LOF method, there are a few terms that must be introduced first. For point A, the k distance of A indicates the distance of object A from its neighbor. The reachability distance of the pair A and B is defined as the maximum of the k distance of B and the regular distance of D of A and B, like the Euclidean distance of A from B. The local reachability distance, or IRD, and LOF are defined as the formulas that you can see here. If LOF of k is bigger than 1, it means that point A has lower density than its neighbors, and it is an outlier which is detected in this way. The last method that we are going to talk about is the one-class support vector machine. In order to go through its details, we must summarize what support vector machines are, which is far beyond the goal of this course. So for more information about this method or any other anomaly detection method, we encourage you to investigate through hundreds of sources online. In one-class SVM, we would like to know whether the new test data belongs to the specific class determined by the training data or not. The algorithm learns a soft boundary in order to cluster the normal data instances using the training set and then using the testing instances. It tunes itself to identify the abnormalities that fall outside the learned region. In other words, we will be looking for functions that are positive for regions with high density of points and negative for small densities, which will be considered as outliers. Finding such a function is equal to finding a separating hyperplane.